Yeah, good evening, everyone. As me is my name, I want to give a brief explanation about the project that I'm doing, one of the classes that I'm taking, mechanical engineering project. So basically, I want to do the final element hardness test simulation on magnesium oxide. So I want to use ANSYS software to do a hardness test, basically indentation on the magnesium sample, and see what's going to be the estimated value for the hardness of magnesium oxide. So I will use the Rockwell hardness test method basically. So there will be a model of the sphere or a board that will be that is going to be called indenter. So it's going to be the one to go into the magnesium oxide sample, and the depth at which this indenter goes will determine the hardness property of this material. So the model that I made is simply 16 diameter of the ball, and this is going to be the formula that I'm going to use at the end of the day to calculate the hardness of the sample. So ideally, Rockwell data square their boss base module already. Their ball base module, as you can see here. So we assume that is going to be asymptotic. We assume that it's going to be asymptotic in the sense that it's going to be asymptotic. So in the sense that it's going to asymptotic. So in the sense that it's going to behave normally in all the directions. So with regards to that, I went to the ANSYS and I make this module. After the module is made, it is meshed. It is meshed to a certain degree in order for me to have certain accuracies. Though I'm using a version that does not support the high resolution, so I was forced to use this mesh. So if I have time to have a smaller mesh, definitely I will have more accurate result. But my version of the ANSYS that I'm using is a little bit restricted, so that's why I use this type of mesh. So during the indentation, the ball is given a certain velocity, so the ball drops into the model with the velocity. So the simple reason for this is that I want to generate a reactive force, because if I use force on this module, on this ball, there's no way I will get the velocity. I mean, there is no way I will get the force again. So I want to plot the stress strain curve in order for me to calculate the Young modulus and the hardness of the sample. So I use velocity in the explicit dynamic. Doing that, I was able to get a distribution, the stress distribution during the loading. So you can see the shape of the indenter goes into the module, and this shows something like this uh, the stress distribution during the loading of the indenter into the module. So the highest concentration of the stress is at the top of the indenter, as you can see here. And during the unloading process, during the unloading, so the stress is showing at the tip or at the edge of the surface of the magnesium oxide sample, simply because there is a compressive force as the indenter is coming up a little bit. That's why we don't have much stress being concentrated at this center again. So we're having the stress being spread out at this point again. So that's just the reason. So calculating the stress and strain for this type of simulation, I was able to plot my stress strain curve. Sorry for this. Plotting my stress strain curve. This gave me a value that I probably need to show you right here. Yeah, this give me a value right here. Yeah, this give me this strength curve when I calculated this with respect to the indentation that I have. So this probably give me a relative close answer to what the Young modulus should be with respect to the magnesium oxide. So finally, I use this formula right here. The formula right here to calculate the hardness value based on the rock wear, and the value as well is much more closer. It's much more closer with respect to the literature uh, data, so within the acceptable tolerance. So this is good enough because we are simulating, we are not actually getting what we should have, but what we are trying to get is something that will be very close to what we should have, and what we have here is much more better. So I got my references from this site, from this books, or from the literature. This is where I got my references. This has been helpful a lot with respect to the simulation and the theory background with respect to the indentation, different type of indentation as well. Credit to my mentor, Dr. King. He has been a good he has been helpful throughout the simulation with respect to the references and guidance that has been given to me. Thank you, Dr. Jing. I really appreciate your help, and thank you everybody for watching my video. So in a couple of weeks I will give you the full detail of the simulation during the in the ANSYS environment, and the way I model and the application of the force and some other things that I really apply. So before I go, just let me hint you the base of this model is fixed. The forces applied to the indenter goes into this module. That's all the boundary condition that I use there in this module. So thank you once again for watching my video. So good night.